So last time the main topic was the dot product. Today the main topic is the cross product. The dot product of two vectors is a number. You can take any two vectors with the same number of components. In other words, whether they be in R2 two-dimensional space with two components, or R3 three-dimensional space with three components, or R4 four-dimensional space with four components, etc. You can take their dot product, get a number. If that number is 0, the vectors are perpendicular. Also called orthogonal. Cross product is technically only for three-dimensional vectors. And when you take the cross product of two three-dimensional vectors, you get a single three-dimensional vector, not a number. Say that again. Cross product is to take two three-dimensional vectors, cross them to get not a number, but one single three-dimensional vector. The formula for V cross W is kind of complicated. To tell you the truth, I never memorized the formula that's in the book. Instead, I rederive the formula every time, which sounds kind of crazy, but I think it's worth doing at least once. I think of this cross product computation as the same thing as calculating a certain 3x3 determinant, a determinant of a certain 3x3 matrix. Certain 3x3 matrix, which is an array with 3 rows and 3 columns. I take its determinant, and that's the answer. Now, if you've had a little linear algebra and you know about determinants of matrices, you know that they're numbers, not vectors. So how can I possibly get a vector out if I do this? Well, it's a bit of fudging, but it gets you the right answer. I'm going to draw a couple vertical lines here, first of all. And these vertical lines, they kind of look like big absolute value signs. Are they big absolute value signs? No. They are a common shorthand symbol for determinant. And determinants of matrices don't have to be positive. So even though these are big absolute value signs, in general, for a determinant of a matrix, you're not going to get a positive number. You could get a negative number. Well, again, here we're going to get a vector somehow. Put I hat, j hat, and k hat across the top of the matrix in the first row. Again, I'm using I hat, j hat, k hat, because that's what I learned from my physics teachers, one of which was Dr. Beacon. He was my teacher. Yeah, he's older than me. Dr. Beacon was my teacher. I took electronics from him. I remember when, fall of 1989. And it was only his second year here. Anyway, where was I going with that? That I learned it from my physics teachers, which included Dr. Beacon. In the textbook, they don't use the hats, right? They use the little arrows. But I can't resist using hats. V1, V2, V3 goes in the second row. W1, W2, W3 goes in the third row. Now, this is not an ordinary kind of matrix. I do have 3 rows and 3 columns. However, the first row is all vectors, not numbers. I hat, j hat, and k hat are not numbers, they're vectors. I mean, yes, they have components. I hat equals 1, 0, 0. J hat equals 0, 1, 0. And k hat equals 0, 0, 1 in rectangular coordinates. But when computing this determinant, I don't even bother thinking about that. I only convert to components at the very end of what I do here. But I learned in linear algebra, and if you have not learned this, I'm about to teach you how to take the determinant of such a 3x3 matrix according to what you might call the standard cofactor expansion. Why standard? Because there are non-standard versions too. But this is just the simplest thing to do. You look at the first row, which has I hat, j hat, and k hat. Take the first entry in that first row, I hat, write it down. Then take your finger or your hand or whatever and imagine creating a new matrix by crossing off that column and that row that contain I hat. The first row and the first column. What's left over is a 2x2 submatrix whose determinant calculation method is something easier to remember. You multiply the numbers on the main diagonal from upper left to lower right, that's called the main diagonal, and subtract the product of the numbers on the off diagonal from lower left to upper right. Say it again. Write down that first entry in the first row, I hat. Cross off that row and that column. You're left with the 2x2 submatrix. You multiply a I hat by the determinant of that 2x2 submatrix, which is easier to remember. You multiply the numbers on the main diagonal from upper left to lower right. That's called the main diagonal. And subtract the product of the numbers on the off diagonal. I could write that in terms of this determinant notation as well, with these absolute value signs that are not really absolute value signs. But I'll just write down what it is here. V2 times W3 minus V3 times W2. That's the first of 3 steps. For the next step, you go to the next entry in that first row, J hat, and write it down, but with a minus sign, minus J hat. You cross off the row that contains J hat and the column that contains J hat. You're left with the 2x2 submatrix. Multiply the negative J hat times the determinant of that 2x2 submatrix. Again, you multiply entries in the main diagonal from upper left to lower right, minus the product of the numbers on the off diagonal from lower left to upper right. V1 W3 minus V3 W1. Look at look at that 2x2 submatrix. And there we go. That's the determinant of that submatrix. Get my finger and pen out of the way at the same time here. I'm not so coordinated. There we go. That is the determinant of the 2x2 submatrix. We've done 2 of 3 steps. The last step is to add k hat. Add k hat, the last entry of the first row. Cross out that row, cross out that column. You're left with the 2x2 submatrix. Multiply k hat times the determinant of that. Upper left product minus main diagonal product minus off diagonal product. Upper left to lower right is called the main diagonal of a matrix because it's a bit more special than the off diagonal entries for reasons I won't get into. That's the answer. And you do go plus, minus, plus. You alternate the signs. This is called the standard cofactor expansion of the determinant of a 3x3 matrix. What's a cofactor? I don't want to tell you. What's non-standard method? Expanding about other rows or other columns. I'm not going to go into details. Most people don't bother learning it these days. But 30, 40 years ago, we did. We're fine with this. The book gives you this as a formula in terms of components. I hat is 1, 0, 0. So whatever gets multiplied by the I hat is what goes in the first component. J hat is 0, 1, 0. So whatever gets multiplied by the J hat goes in the second component. We'll go ahead and write this thing with the minus sign there in front and use parentheses. Though, of course, you can bring the minus sign through the parentheses and write this without the minus sign in front. And then the last component is this. That's the book's initial formula, initial definition of the cross product. They don't talk about determinants of matrices. But they do give you another method to compute this instead of just trying to remember this formula. That's probably the most fun method. I'll warn you though, this method only works for determinants of 3x3 matrices, and not 2x2, not 4x4, not 5x5. Only works for 3x3. You essentially create an array like you see here with I hat, J hat, and K hat across the top. V1, V2, V3 here, W1, W2, W3 here. But you don't bother putting absolute value signs around it. And then you do something strange with this. You recopy the first two columns to the right. Recopy the first two columns to the right. So now you really have a 3x5 matrix, 3 rows and 5 columns. The way you compute the cross product with this method is you consider products along these diagonals getting added to the cross product, and products along these 3 diagonals getting subtracted from the cross product. In other words, B cross W, this product here is I hat V2 W3, the first blue arrow there. It's easier when these are all numbers. The second one is J hat V3 W1. That is a 1 there. The third product that you add is K hat V1 W2. And then you subtract the products along the green arrows. First green arrow gives you K hat V2 W1. Second one gives you I hat V3 W2. Third one gives you J hat V1 W3. Simplify, group together the I hat terms with the minus sign, the J hat terms, and the K hat terms. So we're going to get I hat terms going to be I hat times V2 W3 minus V3 W2. It matches this. V2 W3 minus V3 W2. The J hat term is going to be, look at the purple ones, V3 W1 minus V1 W3, which in there is the opposite of what's in the parentheses right here, because of the minus sign there. And then the K hat terms, V1 W2 minus V2 W1. V1 W2 minus V2 W1 matches this. It does work. It's a bit more fun, more quick, less prone to mistakes if you have actual numbers in here for the V's and the W's. But I wanted to show you it does give you the same answer. And yeah, you don't have to write this one in factored form with a minus sign out there. You can distribute the minus sign through. You can write this with a plus sign there. Even though I had a minus sign here, they are the same. Any way you compute it is okay. Though if the directions say compute it one way or the other, then I guess you should follow the directions. Again, the book doesn't really do this method. it states this formula, and then it shows you this method for computing it. This is the fastest once you get good at it with numbers. Why do we care about cross products? Let's do something kind of interesting. Let's take V cross W and dot it with V, for example. In the general case, the formula that we wrote down, that's the definition in the book. And here I will distribute the minus sign through. So in this second component, I am writing it differently than I did before. I'm distributing the minus sign through. Notice an interesting thing here. Oops. V2W1. The first component doesn't involve any subscripts of 1. The second component doesn't involve any subscripts of 2. And the third component doesn't involve any subscripts of 3. Kind of interesting. Dotting this with V. All right, let's do this messy algebra. I got to do the dot product. So first I multiply these two things. I'll go ahead and do the distributive property right away. V1 times this is going to be V1, V2, W3. V1 times this is minus V1, V3, W2. Then do the product of the second components. V2 times this is plus V2, V3, W1, then minus V1, V2, W3. Careful not to make a mistake. I'm looking right there. Times V2. Then finally, product of the last components being added V1, V3, W2 minus V2, V3, W1. Then something amazing happens. Everything cancels. V1, V2, W3. It's here and it's here. V1, V3, W2. Here and here with a minus sign and a plus sign. Cancel, cancel. And V2, V3, W1. Here and here cancel. You get 0. Likewise, V cross W dotted with W, if you showed all the work, would give you the number 0. In other words, V cross W is orthogonal to both V and W. Fundamental about the cross product. You got two three-dimensional vectors that are, let's do the most common case, that are not parallel. You take their cross product, you're going to get a third vector perpendicular to both of them. So if this is V and W here, my pens, V cross W is going to be perpendicular to both of them. But which direction? Is it perpendicular this way or is it perpendicular this way? As another right-hand rule. Okay, let's say the blue pen is V, the green pen is W. If the orientation is like this, take your right hand, start at V, curl your fingers to W. Your thumb points in the direction of V cross W. But if you switch the blue and the green around like this, now the right-hand rule, V is over here and W is over here. The color scheme is still the same. Now the right-hand rule, you go from V to W, it's going to go like this, and your thumb's going to point in the opposite direction. The cross product is going to be like that. The order matters. V cross W does not equal W cross V. That shouldn't be too surprising when you think about the formula. for V cross W. If you switched around the roles of the V's and the W's, you probably wouldn't get the same thing. And in fact, it's the opposite of what you get this way. V cross W does not equal W cross V, but it does equal the negative of W cross V. The opposite or additive inverse. Likewise, W cross V equals the opposite of V cross W. In other words, cross product is not commutative. Matrix multiplication is another example of an operation that's not commutative. You got two matrices A and B. AB does not in general equal BA. And they may not even look remotely similar to each other. V cross W and W cross V are not the same, but they are related. They're opposites of each other. This is called not commutative, but anti-commutative. Or anti-commutative if you prefer. Anti-commutative. It's not just that they're not equal, it's that they're opposites. Fundamental property of cross products. What are these useful for? We'll see on Friday, they're useful for finding equations of planes. In physics, they're useful for torque. Somebody was asking about torque the other day. Torque is found as a cross product. Effectively, it kind of helps you keep track when you're thinking about torque, applying a force in a rotational kind of way. It helps you keep track of the direction of rotation with respect to whatever frame of reference you're in. Like if you've got a spinning top and you're looking down at it, and you spin it counterclockwise with respect to your orientation. Maybe the torque vector points straight up. If you spin it the other way, it points straight down. But it is with respect to your orientation. So like if the top was on a table and I decided to do a headstand and be upside down, then that would affect how the top looks like it's spinning to me, clockwise or counterclockwise. There's lots of other algebraic properties of cross product. I will come back to those things, but instead, for the moment, let's do something a bit more fun. Let's illustrate an application of cross product. Kind of a seemingly weird application at first, but it is an application nonetheless. Hey, I'm drawing a plane here, not three-dimensional space. Here's a two-dimensional plane. Let me mark 3 points in this two-dimensional plane. Call these points A, B, and C. And let's give the rectangular coordinates to these points. Let's say A is the point 3, 4. B is the point in rectangular coordinates that is, well, how about 9, 2? And C is 9. Well, let's make it, it looks like it might be 6, but let me make it 7. I'll put it up here a little bit more. Any 3 non-collinear points determine a triangle. What's the area of the triangle? Yeah, actually, let me put C over here a little bit more. Let's make it 10, 7, sorry. I want to make it a little harder. Okay, by making it vertical, I made it too easy. What's the area of that triangle? Well, base times height. But what's the base and what's the height? Oh, I mean, we could use the distance formula to figure out, say, this as a base. And then we could figure out this height somehow by right triangles and maybe Pythagorean theorem or something. You have to figure out the length of that side too. It's doable. Should we do it? Okay, let's do it. Let's see. We want to see that we get the same answer. So what's the length of this? It would be the square root of 3 minus 6 squared is 36. I'm subtracting the coordinates. 3 minus 9, I meant to say, is -6 squared is 36. 4 minus 2 is 2, squared is 4. That side has a length of square root of 40. I think that is the base. Which, by the way, the same as 2 square root of 10. Should feel comfortable with dealing with square roots in this kind of way, simplifying them if I ask you to. This is the same as square root of 4 times square root of 10. For this side, 3 minus 10 is -7. -7 squared is 49. 4 minus 7 is -3. -3 squared is 9. Square root of 58. 58 is 29 times 2. That doesn't really simplify. Call the length of the height here, h, by the Pythagorean theorem applied to that right triangle. H squared plus square root of 40 squared should be square root of 58 squared. H squared plus 40 equals 58. Looks like h squared is 18, so h is square root of 18. Square root of 3 times square root of 6. Square root of 9 times square root of 2. 3 root 2. Look good, no mistakes? So it looks like the area of the triangle is 1/2 base times height. One half times 2 times square root of 10 times 3 times square root of 2. It's not a nice number. Looks like it's 3 square root of 20. 6 square root of 5. If I've not made a mistake. Square root of 20 is 20 times square root of 4 times square root of 5. And square root of 4 is 2. So it looks like that's the area. In the ballpark of 15 or so. 16, something like that. There's another way to do it. Use a cross product. Huh? How? Let's call this vector here, I'm trying to draw a vector, V, and this vector here, W. And let's pretend, even though I'm not going to draw it, there's a z-axis coming out of the paper as well. So these are actually 3-dimensional vectors in a 2-dimensional plane. The third component is 0. So V is going to be, what are its components? Looks like 6, -2, 0. And W is going to be 7, +3, 0. What's V cross W? Well, I'll write the answer down after I compute it with the matrix. I hat, J hat, K hat. Copy I hat and J hat again. V has components 6, -2, 0. Recopy 6 and -2. W has components 7, 3, 0. Recopy 7 and 3. Do the arrows. In that way, V cross W in terms of I hat and J hat. For the blue arrows, multiply in a positive way. I get 0, 0, 18K. K hat. For the green ones, subtract the sum of those. -14K hat, 0, 0. These are zeros here. Oh, I hope I didn't make a mistake. Simplify, I get 32K hat. What's the magnitude of that vector divided by 2? 1/2 of that. 1/2 times the magnitude of this vector. The magnitude of this vector is 32. 16, which didn't get the same answer, so I did something wrong somewhere. It's supposed to be the case that half the magnitude of the cross product is the area of the triangle. Probably my problem is back up here, I'm guessing. Why did I write square root? Okay. Square root of 18. Okay, that's good. Okay. 2 square root of 10. 3 square root of 2. 2's cancel 3. 20. It looks right.
It's approximately close.
They're close. Yeah, I mean, this is close to 16. But close is not good enough. We're supposed to get exactly the same answer here. Did I do these calculations right? I used the Pythagorean theorem. Oh yeah, my mistake is in here. I didn't find the base of the correct triangle here for the Pythagorean theorem. That's my mistake. How hard or difficult is that? So we're looking at just this triangle here. The base is not square root of 40. It's shorter, right? Stopping right there. Oh, bad mistake. Let's see. How can we find that length? I knew I was cautious about wanting to do it that way for a reason. I mean, we could try to find this angle and we could try to use trigonometry. Is that worth doing? But to find that angle, we need the law of cosines. Oh yeah, this is really getting into the weeds. I could find this length here to be square root of 1 squared plus 5 squared, 20 square root of 26. I could then use the law of cosines to figure out this angle. And then I could use SOHCAHTOA to find this length and this length, to find the base and the height of this right triangle that I'm trying to apply the Pythagorean theorem to find the height. The goal was to find the height here. I applied the Pythagorean theorem to the wrong triangle to find the height. You see another way?
I was just thinking, could you use like projection vectors to consider a side?
Yeah, you could do that as well. I was trying to avoid vectors, but if I avoid vectors, see, that brings up a good educational point. I'm glad this happened. It brings up a good educational point. Yeah, I could do this by doing what I just said 2 minutes ago. That length square root of 26, I could use the law of cosines to solve for the angle. Once I got the angle, then I could find for this right triangle here, the base and the height. Actually, yeah, I could find the height without the Pythagorean theorem, I guess. I could find the base, and then I could use the Pythagorean theorem as well. Hopefully, ultimately get the right answer. 16 has got to be the right answer. But I also could, as you said, use a projection vector. I could project this arrow along this arrow and get this vector here, find its length. But projection vectors the formula involves dot products. And the formula was related to the law of cosines, like we talked about on Monday. It's all related, but it's more work than it's worthwhile right now. The area of the triangle is 16. 1/2 times the length of the cross product is the area of that triangle. Meaning if you don't multiply by 1/2, you can also think of it as an area. You can think of it as double the area of this triangle, or you could think of it as an area of a parallelogram. This drawing is already messy, but I'm going to add a little bit more to it. These two vectors can be thought of as spanning a parallelogram like this. That would be the parallelogram you'd make when you add them. The cross product has a length equal to the area of that parallelogram, which would be 32. Therefore, the area of the triangle is half of that, 16. Are we going to prove this gives you the area of the parallelogram? I don't think we will here. But I do want to write down another formula that's related to that. Whereas V dot W is the length of V times the length of W. times the cosine of the angle between them. That is an alternative formula for the dot product, not involving the components V and W. Although you need those components to compute these magnitudes. There's a similar kind of formula for cross products. Though it doesn't give you the cross product itself, it gives you the magnitude of the cross product. The magnitude of the cross product is the magnitude of V times the magnitude of W times the sine of the angle between them. Assuming you are taking the angle as we do in standard waves between 0 and pi. Don't think of the angle as being between pi and 2 pi, which, I mean, you could think of you got two vectors. You could think of the angle in a couple different ways. You could think of the angle as being the smallest angle or the biggest one. And that works whether the angle there for the smallest one is acute or obtuse. You could think of the angle as being this or that. This angle is between 0 and pi. This angle is between pi and 2 pi. Think of the angle as being the smaller, if you want to use this formula. Is this hard to prove? I don't think it's super hard. It's essentially trigonometry. But it's something that's useful. It's worth knowing both of these formulas. Notice that V dot W is 0 if and only if the angle theta is pi over 2, 90 degrees. It's 0 if and only if V and W are perpendicular, also called orthogonal. This is 0, this magnitude 0, if and only if theta is 0 or pi. Sine of 0 is 0, sine of pi is 0. Pi is 180 degrees. In other words, the cross product is the 0 vector if and only if the angle between V and W is 0 or 180 degrees. They're parallel, either pointing in the same direction, parallel, or pointing in opposite directions, parallel. V cross W is the 0 vector if and only if V and W are parallel, when they're non-zero at least. If V and W are non-zero, V cross W is the 0 vector if and only if V and W are parallel to each other, if you want to write it like that. Question over here?
Yeah, so the sine, it's the magnitude,
Mhm.
gives you just the magnitude.
The magnitude, yep.
The cross product.
Yep.
But don't we know the direction?
You know the direction from the right-hand rule, so yes, you can still figure out the cross product from that. Yep. What are the full list of algebraic properties of the cross product? Let's just look at it in the book. I said, before we look at these properties, that the dot product is also called the inner product. It's also called the scalar product as well. The cross product, is that also called the outer product? I think some people do. I don't typically call it an outer product. Some people also call it a vector product because the answer is a vector. Dot product, the answer is scalar. Cross product, the answer is a vector. Dot product, the dimensions of the vectors have to be the same, but you can always do that, and you always get a number. Cross product, the vectors have to be three-dimensional. If you're drawing them in a two-dimensional plane, like I just did 5-10 minutes ago, you have to have add on a third component of 0 to do the cross product. And remember, for that example with the area of the triangle, the cross product was a multiple of k hat. It was 32k hat. It's got to be in the z direction if u and v and w are in the xy plane. Here are the algebraic properties. Already mentioned anti-commutative property there. These two are distributive properties. Cross product distributes over vector addition in either order. U plus v cross, in parentheses, cross w, meaning add u and v first before you cross with w, can be found by taking the individual cross products and then adding those vectors. Works with the vector on the left side as well. This is kind of like a distributive property of scalars through vector cross products. You can take the scalar C and put it next to either the vector U or the vector V. Orthogonality properties, U cross V dot U and U cross V dot V are both the number 0. In other words, the cross product is orthogonal to both U and V. U cross itself is the 0 vector because U is parallel to itself. More generally, U cross any scalar multiple of U is also the 0 vector. Any vector cross the 0 vector is the 0 vector. And this last one I haven't mentioned yet. That's called the triple scalar product. If you do U dot V cross W, that's the same as U cross V dot W. Both of these are numbers, by the way, because ultimately you're doing a dot product in the end. Another thing I haven't mentioned is that you can use cross products to find volumes as well. This thing is called a, not a parallelogram, but a parallelepiped. Or some people say parallelepiped. Actually, I think that second way is the more official way. Parallelepiped. It's a three-dimensional version of a parallelogram. If you've got 3 vectors, U, V, and W, I don't see V in this picture. I guess it must be there. It's not labeled V.
Oh, it is just really, really lightly.
Oh, really lightly. There's a really light V right there. This arrow right there is V. U, V, and W are 3 vectors that are not all in the same plane. It's called linearly independent for those people who know linear algebra. If you got 3 linearly independent vectors, not all in the same plane in 3 dimensions, they span a parallelepiped. You can make a three-dimensional object spanned by those 3 vectors. What's the volume of that? It's the absolute value, that's absolute values there, of U dot V cross W, the triple scalar product there. Amazingly. Since these cross products are related to areas and volumes, besides what we're going to do on Friday in applying cross products to finding equations of planes, they're also useful for thinking about double and triple integrals. Since cross products are related to areas and volumes, we will see near the end of the course that they're also related to double and triple integrals. Single integrals find areas under curves. Double integrals find areas under surfaces. The surface above the XY plane. What's the, I meant to say volume. What's the volume under the surface? Triple integrals, what do they find? They find hypervolumes above 3-dimensional space and below a 3-dimensional hypersurface in 4-dimensional space. I'm serious. Now, nobody can visualize that. I mean, I said the words, but I can't visualize it. They are useful. Triple integrals are useful. Okay. Instead of areas under curves or volumes under surfaces, they are hypervolumes under hypersurfaces in four-dimensional space, under those surfaces, yet above the 3-dimensional space that we live in somehow. Okay, but they're useful. They are useful.